Hello and welcome to this bonus session, which is an introduction to illumination. And we're going to look at the basic factors of light through its history, its use and design. Student book page 71 to 74. Okay, don't forget the supplementary book Environmental Science in Building, Randall McMullen, will give you further understanding. Within this presentation also I've got some links to some fantastic resources. I've actually put them as handouts within your team's class notebook, so do take a look in there. There's one on human comfort, which looks at everything that you should be studying on the unit 1, and another one in particular with daylighting design factors, so be sure to check that out. So one of the things that we need to look at, or you need to look at, and I'm going to show you this first section of this session. I want to just touch on a few things about the exam. You'll see shortly some exact questions taken from previous exams and the kind of stuff that you will expect to see. So every year in the exam series, whether it's January or June, there will be illumination questions, and perhaps they will say, what would you consider offering to the client for a swimming pool? You need to take a look at this: incandescent filament, my apologies, fluorescent lighting, discharge lighting, solid state light emitting LEDs. They will expect you to know what they are and what would be best used. Now, this is not a lesson that I'm going to do. I'm not going to do a lesson on light bulbs. So what you really got to do is start looking at the information that surrounds you in the learner's book, the student book here, the sessions that I do, of which I say I don't go into light bulbs. I just do the underpinning science of it. And the handout resources that I've given you, some further research and study is required for this. So these questions are taken from the January 2018 exam. And these questions are all from that exam. So one of them: explain 2 reasons why the architect will need to consider glare when designing the retail unit. So ask yourself this question: what are you going to say? What are you going to say? This is worth 4 marks. A very easy question is 2 points. This is 4 points. So 2 points per reason. But if what would you say to that at this point in time? You probably wouldn't know what to say because you haven't studied that yet. And this is why I'm saying to you, expect the unexpected. We've got another question here: the fast food restaurant. So as part of they've given a scenario, and I've extracted this from there. Some restaurant that's being designed, and you're doing illumination design for the fast food restaurant, and it'll have a sign illuminated by a floodlight. The intensity of the light is 300 candela. So you can see that this is the scenario here. Now this is the angle of light. This is Lambert cosine law, of which you're going to do in the second session. You're going to do a basic stuff with me, then you're going to do the merit level exam question with Josh. Explain 2 methods of increasing the luminance of the sign. So how are we going to do that? Well, I'm not going to tell you. I mean, I will inadvertently tell you through the second lecture for illumination. But please remember that this bottom question here, it says calculate the illuminance and point to X on the sign. So this is the kind of thing that you need to know. Interestingly, I've gone through the exam questions. Now, I've put all the exam papers in from January 2018 right through to June 2019. Or January 2020, sorry. And it's only on this one where they've actually asked you to calculate. Now, I'm not saying don't expect a calculation in January 2021 exam, the one that you'll be doing, but just prepare yourself for a calculation. I don't know what to expect, but I would be prepared to do that calculation. Now, in the second session, when we look at this, you'll be able to calculate this. Okay, but at the moment you don't. So please be aware that you need to take in as much as possible through the handouts, through the books, student books, and the environmental science book to help you along the way with this. Looking at the January 29 series, so there were only 2 questions on there for illumination. State one performance related benefit of using discharge lamps in a shopping centre. So what would you say to that? At this stage, you would be guessing. But in an exam, they would expect you to know. And interestingly, the bottom one there, the client is concerned about lighting levels in each part of the buildings. Discuss how different lighting levels may be needed depending on the use of each area in the building. So we're looking at fit for purpose. We're looking at the kind of tasks that are expected to be carried out within the buildings. Obviously, the building from the scenario they've given. But look at this. Look at this. 9 points that's worth. That's huge. That's in the grand scheme of things. That's a massive amount of points. So if you can discuss, I mean, what they mean by discuss is, it's kind of point out all the different points that the client would need to know about, and how would they be, how the challenges of the lighting in different areas, how those challenges would be met with your offering. Here we got the January 2019, so we have a construction company plans to incorporate natural lighting into the new industrial unit. Explain 2 benefits that natural lighting would provide. I mean, I can think of a multitude. If you actually look at the handout that's entitled Daylighting Design Strategies, it's all in there. And it's a really, really good presentation. It's by Dr. somebody, I can't remember the name, but I mean, there's no point me trying to rewrite what he said. I'd be wasting my time because his presentation is absolutely spot on. It's everything you need is there to answer that question. That's 4 points. If you answered that question and the previous one, 13 points already. The next question there, the railway line will have stations for passengers to get on and off the train. At each station, a minimum level of luminance is required. So describe what is meant by the term minimum level of illuminance. That's a very straightforward question. It's worth 2 points. Effectively, the term minimum level of illuminance is that enough light to carry out the task. I mean, you'll need to put it in a little bit more detail than that. Don't write your sentences so short that they're so abrupt that the examiner feels that you haven't really answered the question at a level, at level 3, this level. So 2 more questions. This is the January 29. Again, the scenario is a gym. It has LED lamps attached to the ceiling by 1500mm long steel suspension cables. Question B is the snack bar will be illuminated by fluorescent tubes. Explain 1 disadvantage of using fluorescent tubes to illuminate the snack bar. And it's a very simple answer. It's worth 2 points, but you should know the answer to that. And look at this one. 6 points on this one. Look. So the construction company wants holiday homes to make best use of natural daylight by making sure the daylight factor is high. Now you need to explain 3 ways in which the daylight factor inside the holiday homes could be maximised. So again, look at that handout, the daylighting strategy handout that I've given you there. That again, it shows you a multitude of different ways in which that could be met. So if you can't answer that question in the exam, you haven't been looking at the resources that I've been providing to you. Now, here are 3 links. The first one is designing buildings with wiki lighting. Now, Wikipedia, I'm not a big fan of Wikipedia, if I was to be very honest. I'm just not. It can be edited, it can be authored. Sometimes the information can be slightly inaccurate. But when it comes to the science side of stuff, you look at, you've got the ICE, the Institution of Civil Engineers, you've got the Chartered Institute of Building. These are big professional bodies that they're happy to sponsor and support the wiki lighting, the wiki construction site. So it's a really good resource, and that site there, that first one, it goes into so much detail. There's so much stuff there. It's you could spend days just reading it. It's that good, and it's got a very good index where you can go straight to the point where if you want to go to daylight factors, it'll have a little it'll have a link, hyperlink straight to that. You can go. It's very well laid out, so take a look at that. Then we've got the HSE. Okay, what does the health and safety executive say? So we're talking about human factors, lighting, thermal comfort, working space, noise and vibration. Everything's there for this exam. Human comfort, that's what you're going to be tested on. human comfort, structural mechanics, and the properties of materials. So you're halfway through the human factors part of your unit. So why not start taking a look at this website and start seeing what's that, and cross correlate with different websites and the handouts that support it and the books that support it and whatever I say that supports it. You've got everything you need. Look at this one, CIBSE, which is the Chartered Institute of Building Service Engineers, and that link there takes you to what they do in terms of lighting in buildings. So what about the spaces that they light? How do they do it? How does CIBSE do it? I mean, they are the the number one chartered institution for lighting. Obviously for sound as well and ventilation, etc. But those are three really good websites that you should be going to frequently, not periodic, frequently. So this one here is this is getting onto the underpinning knowledge now about illumination itself. So back in way before 1879. In fact, if we go all the way back to caveman times, when we first made fire, that was our obviously fire had a lot of bonuses and advantages in creating tools, but it also you could cook food in a very raw and basic sense, but it also provided heat, which provided human comfort, and it also provided light. So you're in a cave or you're out in the open and you're exposed to danger with all sorts of things that wants to eat you. Fire was a really effective tool in terms of survival. So through the ages we went from that, and then we invented candles, and candles right through the Middle Ages. They lit monasteries and castles and big homes, and they lit street lighting. They had street lighting, which was candles, because they used to have a chap who used to, in the mornings and the evenings, he used to walk the streets of London, for example, lighting the candles in the morning or early evening, and then in the morning he would douse them out. I can't remember the name of the person that did that, but he had a long rod with like a metal cone on the top of it that he used to place over the flame of the candle, and then he extinguished it. And then we went to gas lighting. So gas lighting, that was brought into actually brought into the homes, where it was revolutionary. You didn't have the issue with the candles. Obviously, once a candle is burnt completely, then you don't have any more fuel for it. Paraffin wax, as it was, that created candles. But gas was a never-ending supply of it. And as you can see here, Edison started the whole thing going. Well, I don't know if you've seen the film about Tesla, but there's a backstory to this Thomas Edison chap, where effectively it was Tesla who invented AC electricity. Edison actually produced what was called DC direct current, of which was lethal. And they were at the same they were trying to produce an electrified circuit for cities at the very same time in history. They were both existing together. In fact, one worked for the other one at some point. But the story goes that Edison, what he actually did was he stole Tesla's idea how to produce AC electrics, alternating current, which was far safer, and electric that we still use today. And Thomas Edison was credited for it. It was actually Tesla. It was East European descent. I can't remember his first name now. But there you can see that difference. Like the sodium lamp was first produced by Philips, 1932. It just gives you a bit of a timeline all the way up to blue LED was discovered by a chap in 1993. So let's just give you a bit of background about lighting itself. Now, one of the things about light, so daylight is actually is known as white light, and the white light is obviously has the spectrum, the colours of the spectrum within that white light. But because the light is constant, we don't see all the different colours at the same time. We just perceive it as white light. But if you put it through, say, water, at a certain angle, or certainly a glass prism, it's broken up into the spectrum like that as you see it. And if you can get it, glass prisms, you can get them on Fleabay very, very cheaply, a couple of quid. You can put lights through it in yourself. And the best way to do it is in like, if you create what's called a light box. So it's effectively a pitch black box, and you would have a pinhole that you could view through, another pinhole where you would shine light through a prism onto the black surface at the back of it, and then you'll be able to see. It's absolutely fascinating when you see it for yourself. But the thing about the thing about this, what we've learned from breaking these the spectrum down into its individual colours is quite fascinating, and I'll show you how. Now, at the top there, you can see the visible spectrum. Okay, so that's the spectrum of all the colours that we know, so the complete range. None of you would be any stranger to that. And the fascinating thing about this is that often you hear about planets or stars that are hundreds of billions and sometimes trillions of light years away. And we know a lot about that particular star that's so far away because of light. So when we talk about a light year, it's the amount of, it's the distance that light travels within a year. So if I believe light travels at something like 330,000 meters per second, which is quite a lot. It's 33,000 kilometers per second. Now, so that means light travels around a planet a couple of times within a second. 2 or 3 times in a second it'll pass around the circumference of the planet. That's how quick light is. And it's stated that nothing actually travels faster than light, but there is something that's called tachyon, of which I've known about for some time. That and that's spelled, if I can just get this right here. Now maybe, I believe that's the correct spelling, tachyons or tachyons, or however you want to pronounce it. But apparently science is putting forward the idea that that is actually even faster than light. And the problem we've got is this is what's associated with time travel as well, that if you can't travel faster than light, then time travel is not possible. Well, certainly not into the future, but what you can see into the past, and we do that every day. They've got the Hubble telescope that's out there in space somewhere. So what happens is when the Big Bang happens from a central point in the solar system, from a piece of space in time, it exploded out, and obviously the galaxies were formed, but that explosion is still continuing somewhere out there in space. So the Big Bang actually is still existing, because as it grows, it creates more of its solar system, its super galaxies. All of those things are still being formed. Now, if you point a telescope in the right direction, you can actually see back, billions of years into the past by looking at the light in that particular part of the universe, and then you can analyze that piece of light. But more interestingly, when they say, Pluto as a planet has been downgraded as a planet a few years ago, but nonetheless, if you look at Pluto, they can say there is this much hydrogen, there's this much neon, there's this much iron, there's this much copper, there's sulfates there's sulfur. And then you think, well, how do you know that? We've never been to Pluto. But so what they do is they actually analyze the light that is reflected from Pluto. So as that light is received on Earth, we put it through a prism. And when we put it through the prism, you can see these signatures. So if you look at the iron, for instance, that is the light signature for iron. And it's like a barcode. It's very, very, very specific. No other signature will look like that. So when we analyze light that comes from other planets and from trillions of light years away from the Big Bang, we can actually analyze the component parts of that light, and so we can tell what gas and what minerals and what particles are actually present at the Big Bang. And it's all through light. So light is a very fascinating thing. So a little bit nearer into our immediate past, something to do with building regulations was something called ancient lights. What this did, this is actually a real fascinating story. It, it says here, another factor considered with regards to ancient lights. Oh, sorry. If we start at the top, the owner of a building with windows that have received natural daylight for 20 years or more is entitled to forbid any construction or other obstruction that would deprive him or her of that illumination. So neighbours can't build anything like a big, huge conservatory next door. And this is absolutely part of the building regulations today. Is that when you have a neighbour who wants to access planning permission to build on the side of a house or the back of a house, some structure, then the neighbours can actually challenge that, and then they can come out. And sometimes when structures are put together and they've been given planning permission, and then the neighbour next door sees a noticeable loss in light in their own house, then there's a serious legal issue there because of the ancient lights law. So another factor considered with regards to ancient lights refers to the building surroundings rather than its residents. And what they actually say, I love these old laws and bylaws, where it says that the convention basically is that if an old building which is marked with ancient lights, so you can see those 4 houses there with the ancient lights on there, if that's all demolished, then the new building which replaces it cannot be of a height higher than that of the original building. And that's obviously because the higher you build the buildings, the more light it's going to block out with surrounding structures that might be affected, and those ancient lights affected as well. In 1695 in England, there was a window tax which became law a little bit later on in Ireland. And effectively, a glass tax was introduced in Ireland in 1825 and endured despite protest till 1845. So what they did in England and Ireland, let's go back to the 11th century with King James and the what they called the New Bible, the what do they call it? The New Testament. Effectively, what it was is that King James had the scriptures, which was apparently was a set of ancient documents that was, I don't know if it's folklore or whether you believe this or not. That holy men put together in the time of Jesus, and these were a kind of set of laws and principles directly drawn from the Bible, the way that people should live, etc. There was nothing about a window tax in there, by the way. But what King James did was he had the Bibles produced, and then those Bibles were given out to people in some short form or another. And what that meant was that if you owned a Bible, you had to pay tax. So, of course, what people did then is that they started to change religion to avoid having the Bible, the Christian Bible or the Church of England Bible. And they say, well, I'm a Roman Catholic, so I shouldn't pay tax. So throughout time, different governments of countries, they tried to come up with different ways of taxing people. So the window tax was quite interesting, where you can see the examples here, the top two. You can see that the one on the left is clearly it's a building in London of a very, very noble stature. It's Georgian, and that the windows were all bricked up to avoid paying tax, because the more glass space you had, the more square meterage of glass, the more tax you paid. And you can see the same on the right hand side there. And what's really interesting is the bottom picture is actually the Bank of Ireland in Dublin, and that's how it looks now. And you can see those windows were blocked up, and they're the bank. They're the ones that had all the money, but they were blocking the windows. One thing to mention as well is before this they had something called a roof tax. And if you've ever been to Republic of Ireland, certainly you will drive around and you will see an awful lot of cottages and old buildings with no roof at all. But people living in the houses, or they were, many years ago. And the roof tax was the same, as that if you had a roof, you must pay tax. So of course, let's burn the roof down. Let's take the roof off, and then we'll live on the ground floor. And that was a way of avoiding tax as well. So, but the window tax obviously had a direct impact on human comfort for obvious reasons, in terms of human comfort by not receiving light, and it's all about the well-being of a person, the human comfort. Obviously, having enough light to carry out tasks within inside the building was really important. So, as I said, the resources on Teams right now. Okay, So illumination, acoustic daylighting design strategy. Now I'm just going to quickly come out of this presentation because I want to show you. I want to show you. Now this is what they call SlideShare, and it's part of LinkedIn. If you get a membership with, well, it's not a membership. If you sign up to LinkedIn, then if you've got a LinkedIn login, then you can do this. So what I've done, this is one of the resources here. I've just typed in human comfort, okay, and there's various all sorts of stuff on here, all sorts of stuff. But if we click on this, this is absolutely brilliant. And I've downloaded this and give you this as a resource. So just quickly going through it, you'll recognise some of this. Obviously, we're talking about heat. We've got temperature, humidity, noise, light, smell, temperature. These are all things that affect human comfort. You'll recognise this, won't you? All of you. It's a psychometric chart. So thermal comfort, design strategies. You can see the solar gain there and thermal mass. You can see the way that the footprint of the building is, where it's positioned. Solar heat gain, you'll know about natural ventilation, passive ventilation. Yeah. Visual comfort, what we're doing now. And they're only small slides. They're only small slides. So why wouldn't you go and have a look at it? Look, daylighting. Look at this. This will help you for your exam. If you don't read this and take notes from this and just investigate a little bit further. I mean, here, look, you can see that a lot of light, so we've got an obscured glass there, has a different effect to big open windows like this. In the old days, Georgian houses that used to have lots of glazing bars, I mean, lots and lots of glazing bars. What they did, they actually had them taken away and they put sash windows in, which is a little bit like this, where so much more light came into the room. But then you got something like this, which is aesthetically it's nice, but it's taken out a lot of light that's naturally coming into the house. We've got the acoustics, design strategies for acoustics. This is from last week's lesson. I mean, you've really got to look at this. This is about smell, human comfort. This is all excellent stuff. It really is such a now this one here is the one that we're talking about today. This is another handout resource that I've given. It's Dr. Abdul Tawab Katan. Okay, so obviously he's done his PhD, but this is really good stuff. This, I don't know if you can just I mean, all of these things here are covered, but the way he's done it is like a level 3 way of doing it. It's basic stuff. Energy savings with daylighting. Energy savings got anything to do with exam questions that I read out earlier? Of course they have. These are another positive factors: windows and view, productivity and satisfaction, controlling daylight in interior spaces, minimize glare. We've got strategies about design. This is really good stuff. Building orientation. Look at this building form. So instead of just building a normal house where in the centre of the house you don't get no light, if you build long and thin like this, then you're bringing in light from from each of the shapes. They're just surrounded by light. Really effective way of designing. This is the effect of building on the environmental control strategies, how we talk about daylighting and heating and cooling in different shapes of buildings, give you a better understanding of a better way of designing. Illumination, roof geometry. This is really, really, I mean, it's a fantastic resource. This is really such a good, I mean, why wouldn't you use this as it's got everything you need. All of the skylights, look. Different examples. It's an absolutely fantastic resource. So I'm going to come out of there and I'm going to go back to the presentation. So those are in there now. Okay, those are in there now. So let me get back to there. There we go. So they're on Teams right now. So after you've seen this lesson, go and go through a couple of those. The one on the left is the most obvious one for today's session, illumination. But it says illumination acoustics, but I haven't gone all the way through it there. I've just gone through the illumination stuff, and I think it's just brilliant. So help yourself to that and get yourself linked in. As soon as you do that, you can go to SlideShare, and there's a huge amount of resources with presentations like this. It's a brilliant resource. So some of the other positives we saw recently, like Windows and View. But what about vitamin D? Where the synthesis of the body producing vitamin D with the sunlight creating that reaction once it hits our skin. It's all part of human health, isn't it? Productivity and satisfaction. We've got the efficiency and cost, which is obvious. So the more daylight we can get into a house, the more cost effective it is. It's efficient. It's fit for purpose. No fuel is needed. And we look at that there, the daylight factor. So it's 100 times the internal divided by the external. So the architect and the design team there will say, well, we'll need, say, 450 lux. Well, I'll explain lux in the next session, but it's the amount of illuminance that's received at the surface. So, for instance, if you're just walking down a corridor or the back stairs of an exit in a building, it might be just 50 lux. In a classroom, it might be 250 or 300. And then we start going up, like shops could be 750, so it's nice and bright to show off their various products. Then you got 1,000 in hospitals, in surgery areas. Obviously, you want the surgeons to have a lot of light, and then it goes up to fine artwork with watchmaking. Could be, in jewelry production, could be 2,000. So with that daylight factories, what it's actually saying is how much internal light can we bring in from the external. So how much external light, the more light we get, we need less internal light, so which will be cheaper in the long run. It will be cheaper to run the lighting in the building. It provides enough resources without having to produce electricity from fossil fuel or photovoltaics such as solar panels. That will equal the daylight factor. So wherever the architect prescribes, that's how we can work out how much electrical light, internal light, that we'll need to provide. As part of that, we have something called seasonal hours. So this is the average monthly daylight in the UK. And when you look at, let's say, December, you've got 1, 2, 3, 4, 5, 6, 7. You've only got 8 hours on an average of daylight in December and January, and then obviously the longest day in July. You've got about, let's go on, let's have a quick count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, sorry. What was it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 and a half hours. There's only 7.5 hours of darkness. I mean, I'm a big golf fan, and quite often in the summer I get up at 3 o'clock in the morning, and I'm teeing off at 3:45 in the morning because the sun's risen and it's looking really nice, really nice. So, but we need to understand about seasonal hours where this is going to differ from, say, down in London up to Glasgow in Scotland. That it will differ. The sun goes down very quickly in winter time, so therefore we're turning on illumination, we're turning on electrical lights to supplement the daylight hours. So that's also something that we need to understand when we're designing buildings. So that's the end of this presentation. So that's just something that was in one of those presentations that I just showed you there. It was just highlighting it. It really is it gives you lots of different thoughts and ideas about how we do design for buildings with daylight, and these are better type designs of buildings. Obviously, this doesn't really work with terraced housing and domestic housing. So this is more about, corporate buildings, commercial buildings that would have a huge amount of requirement for lighting, depending on its purpose, and so would design in that way. So you could say that the one that looks like a W, you could say that's offices. So you're getting the light in from the left side and the right side and the top side and the underside. You're getting it from everywhere. And if you actually incorporate what we call light tunnels, which are basically extended light panels in the roof. What's the word I'm looking for? It's been that long since I used that word. The skylights. So it's just natural light coming in. But what they do with the skylights, they use reflective materials to take them down 3 or 4 floors. And if you look at something called the Eden Project, and especially a guy called Michael Paulin, who's fascinating. In fact, his name, I went to see him at a symposium in, oh, we've done it again, a symposium in London a few years ago. His name is Michael Paulin. And he did what's called biomimicry, which is effectively the science and architecture of imitating natural surroundings, plants, insects, and designing in a natural way. And he was the principal designer behind the Eden Project, which are those big, massive glass hemisphere type structures where they've got an eco structure existing inside of these structures. And he's actually worked on projects like bringing, fertile grass plains to the Middle East, into the deserts, by using these methods. And one of them was a building which, using a complex alignment of reflective materials, he was bringing natural light down, some 100 meters down into the bottom of a structure, an open plan structure, where there was probably something like 5% of the total lighting needs for the building was provided by fossil fuel or photovoltaic energy. The rest was just normal daylight. So yeah, check that guy out, Michael Paulin. Very, very interesting. Loads of stuff on Talk TED. So check him out. So the next session is going to be about the mathematics behind illumination. So we're going to be looking at the E equals I over D squared, which is the inverse square law, and then we'll take a little bit further to Lambert cosine law, which is E equals I over D squared cos theta. Thank you.